Okay, these next two examples show the action of a force acting on a mass over a distance. We're not saying whether the mass is moving over a frictionless surface or not. We're simply looking at the action of the force itself applied to the mass as it moves over a distance specified here as 5 meters. Now we're going to look at two examples. The first looks at the case where the force is acting in a direction parallel to the motion, and in the second example we're looking at the case where the force is acting at some angle, in this case shown as 35 degrees, to the motion, but the object still moves in a direction horizontally. Now in order for that to happen there must be other forces acting, and in this case obviously there's a weight force, possibly a frictional force and a normal reaction force as well. But the question does not involve those forces, it simply looks at the action of the pushing force and how much work is done by that force alone. So let's look at the first of these two examples, which asks us to calculate the work done by a 40 Newton force acting on a mass over a distance of 5 meters in the direction of motion. As I indicated, force is parallel to motion, so to calculate this we simply use the formula work equals force multiplied by distance. Doing that, we've got 40 newtons multiplied by a distance of 5 meters, and that gives us 200 newton meters or 200 joules. Now this question has been simplified because we've called d distance rather than displacement, but the technical definition of work done by a force is actually a vector dot product between a force vector and a displacement vector, which we are now going to look at in the second part of the question, where the force is not acting in the same direction as the displacement, or the motion in this case. Now notice that I've got displacement shown as a single arrow rather than a double-ended arrow. That's because we're now going to do the same question with the force acting at 35 degrees, and the component of force acting in the direction of motion is the part that actually does the work. That is the part that can possibly accelerate the mass in a direction parallel to its motion and therefore increase its speed, and later on, as we will see, this increases the kinetic energy. If we show this solution, we'll see that the F cos theta represents the component of force in the direction of the displacement, shown here still as a d. So we have 40 times cos 35 times the displacement of 5 meters, giving us, rounded to the nearest whole number, 164 joules. So we note that is less than 200 joules because not all of the force is acting parallel to the motion, only part of it is. Interestingly, if the force were acting perpendicular to the motion, in this case straight up, then theta would be 90 degrees, therefore cos theta would be 0, and we would have 0 work being done. And you might ask, how is this possible? Well, the only way that that could happen is if the object were already in motion and it was on a surface where, say, it was frictionless and it continued to move at a constant speed, not speeding up or slowing down, and the force was acting perpendicular to the motion, therefore had no component in the direction of the motion which could change the speed of the object. We'll look at different situations in the next example.